So the purpose of this is we want to determine the percent KClO3 in an unknown solid. So the solid is going to contain KClO3. KClO3 is, what's the name of that stuff? It's potassium chlorate. Plus other stuff. Now, we need to know what the other stuff is, to the extent that the other stuff can't react with how KClO3 is going to react. And so the other stuff is inert. Here. And so what we can do is we can just analyze for the KClO3 alone. And the analysis of KClO3 is kind of reactive. It's not the most stable stuff around. Why would you suspect that KClO3 is somewhat reactive? I wouldn't suspect, as far as metathesis goes, group 1 cations are really unreactive. So potassium ions from metathesis, they don't really precipitate with anything. Just really exotic species might precipitate. As far as acid-base, potassium ions, are they very reactive in acid-base reactions? Oh, it's soluble. But potassium ions are neither acid nor base, so we call them neutral. What about redox? What do you know about potassium ions and redox? It's like the second weakest oxidizer on the chart. This is weaker than lithium ion. Or no, it's actually a little bit stronger. Lithium ion is the weakest, so potassium ions would be a little bit stronger, but a little bit stronger is nothing. We don't really worry about oxidation due to potassium ions because they're so weak. However, chlorate's a bit more reactive. What do you know about chlorate? Well, chlorate's not on the chart. So if something's not on the chart, what would you do initially to get an idea of how it might react? In redox. We could do its half reaction, or the other option is well, actually, before doing the half reaction, this is what I do, because if we do the half reaction, we need to know what the major product is. And that would be a bit of a guess. I mean, you could guess different things for the major product of chlorate, like oxygen and chlorine and whatnot. But probably all we're going to do is just look at the oxidation states. So potassium, chlorine, and oxygen, which one goes first? Normally oxygen, but oxygen being the most electronegative, but the group 1s go first. And so potassium always goes first at +1. Basically, if potassium is going to have a charge, there's only one charge available to it, whereas chlorine and oxygen could have other charges that are available. And so chlorine versus oxygen, who gets assigned next? Oxygen at -2. And that means chlorine is +5. And so we can see -2 times 3 is -6. -6 plus 1 is -5. So to cancel out that -5, we need a +5 because compounds are neutral. They have zero charge. And so when you see chlorine in a +5, chlorine doesn't really like to be in a +5. Chlorine much prefers to be in a what charge? -1 charge. That's what chlorine likes. And so we would think of this as being an oxidizer, i.e. oxidizer is electron poor, or reducer, which is electron rich. I'm sorry? It wants electrons, so that's an oxidizer or reducer. Reduction is gain. It wants electrons, so it's going to undergo reduction, but itself, it's an oxidizer. And so we see that this is going to be an oxidizer here. But if we have an oxidizer, we also need a what? Reducer. But this other stuff is inert. There's no reducers in the other stuff, or at least reducers that are strong enough to react here. And so what we're going to do is we're going to do this. We're going to heat this up. We're going to heat it up, and when you heat it up, then you're increasing what? Kinetic energy. And you know, normally KClO3 is what we call an ionic lattice. So the chlorate ions are located in the lattice, and the potassium ions, and they alternate. So you have chlorate, potassium, and they form this lattice structure. But as we heat it up, what can happen? You got what types of motion? You got vibrational motion. You could have vibrational motion within the lattice. So the potassium ion and chlorate ion, they're vibrating. And then chlorate itself, you know, when you look at the Lewis structure of chlorate, you got a chlorine in the center and then these three oxygens bonded to it. Like this. We have different representations of Lewis structure for this. This is an expanded octet here. I mean, we could expand the octet one more to get it, or we can just go with an octet. We'll be talking much more about this later. If we just go with an octet, then I'm going to put all single bonds. And what I have circled here are the formal charges. And so sometimes we'll expand the octet to get rid of those formal charges. Chlorine is one of those elements that are capable of expanding its octet. Do you know which element is not capable? Which elements are not capable of expanding their octets? The second period elements. So, but anyway, regardless of which Lewis structure you prefer, the oxygen and chlorine bonds will be vibrating as well. So this whole thing will be vibrating. And so the vibrations usually, you know, the oxygen and chlorine bond distance will change like this as it vibrates. Yeah. So as we heat it up, and then we add something called a catalyst here. And the catalyst we're going to use is MnO2, which is black powder. This is it. It's MnO2 is called manganese. Not manganese 2, because oxygen's -2. If oxygen's -2, that means manganese has got to be +4. So we call this manganese 4 oxide. That's its proper name. This bottle is labeled manganese dioxide. A lot of people call it manganese dioxide too. If you look at like sandstone, red sandstone cliffs in the desert, sometimes they have a black coating on them. The black coating is called desert varnish, and manganese dioxide is desert varnish. So we had a catalyst. Do you know what catalysts do? They speed up the reaction. So what we're doing is we're trying to heat this, and what we're trying to do is we're trying to get the oxygens and chlorines to vibrate like this. But sometimes that needs a little bit of help, because do you know what's going to happen? Which one's more electronegative, the oxygen or the chlorine? Oxygen's more electronegative. And so oxygen doesn't want to give up its electron. Remember, oxygen is happy as is at -2. But when you look at chlorine, chlorine's pretty unhappy because it wants 6 electrons. And so what happens is we heat it up in the presence of the catalyst, the chlorine, and this normally wouldn't happen, the chlorine actually oxidizes the oxygen. And that's only going to happen if we heat it up and there's some violent, kind of collisions, because not all the atoms are moving at the same vibrational frequency. Some will be moving at a much higher frequency, and it could cause this reaction to occur. And the reaction is that the chlorine is going to take 6 electrons, and we're going to form potassium chloride, solid, where the chlorine goes from +5 to -1. Where did those 6 electrons come from? Those 6 electrons are going to come from the 3 oxygens. Each of those 3 oxygens are going to lose 2 electrons. And so we're going to have 3/2 O2 gas form, in which we'll have 0 oxidation state here. Is that 3/2? Yeah, 3/2. So 3 oxygens here, each of those loses 2 electrons, and we'll end up with 3 oxygens at 0 oxidation state. And so this is called well, it's not a molecule. This doesn't form molecules, but if this did form molecules, we'd call this an intramolecular redox reaction. A redox reaction happening in the same species. We see this in other areas as well. This one is not so easy. This is why we have to heat it up, because it's not normal that chlorine oxidizes oxygen. Oxygen should oxidize chlorine. That's normal. But when we heat this up, we can get it to go up. And then once you drive off the gas, it can't reverse back down. And since this is a sluggish, KCl is fairly stable in the presence of oxygen. And so the catalyst helps us. Otherwise, this stuff doesn't really decompose. Oxygen is not easy to oxidize. Yes? Can I read what? Beneath the, okay. Let me take a look. Let me find out. This triangle means heat. We heat it up. This is a common symbol for heat. In the presence of the catalyst is MnO2, which is manganese 4 oxide or manganese dioxide, and the appearance of this is a black powder. You don't need much of this. So this is what we have to do. We'll get our sample from the stockroom. Make sure you record the unknown number. It's written on the cork here at the top. So I have unknown number 40. Record that into your lab notebook. And then all I'm going to do is I'm going to go over to the stockroom and I'm just going to tare this. Just have a little holder beaker for your test tube, large test tube, and then just zero it. And then we're going to tap in the desired amount of sample in here. And then weigh it. We need to know how many grams of white powder we have in there. Okay, then I'm going to get my catalyst, and I'm going to get a little bit on the tip of the spatula. So you need like a match head's worth, you know, or less than a match head. Are you guys, like, if you look at our match book, about that much, just a tiny bit of catalyst in there. And then you're going to drop the catalyst into the white powder and then shake it up. We don't have to worry about it reacting right away because it's going to need some heat. There's a little bit of barrier for the reaction. So we end up with a gray, kind of a gray powder after mixing it up. You want to try to mix it up thoroughly, you know, with the white powder just by shaking this. But we need to know how much of the catalyst we added in there. So after we add the catalyst, we're going to weigh it again. So we're going to take multiple measurements, weighings, so that we know how much white powder there is and how much black catalyst there is in our test tube. All right. You don't have to worry about leaving the fingerprints on there, but if you do it repeatedly, then, you know, it's all right. If you touch the test tube, you're zeroing it anyway, and so I wouldn't worry about it. You zero it and then tap it in. But if you're touching it and then putting it back on, let's say I zeroed it, then I grab it, and then add the catalyst in there, and then put it back, then you're changing the weight. And so there, if you're going to grab it and take it off, then use a paper towel or a Chem white tissue to avoid fingerprints. So it depends on how you do it. I would just probably just leave it on the balance and then just tap in a little bit, but there's a problem. If you leave it on the balance and tap some in and you accidentally spill some on the pan, then you just screwed it up. You screwed it up because then it's no longer tared properly, the balance, and you'd have to start over. And so it might be safer just to take it out and then tap it in off this. It depends on how you feel, I suppose. All right, so we'll do that, and then we're going to heat this up and then allow the chlorine in potassium chlorate to oxidize the oxygen to create these as a product. We're going to generate oxygen gas. Then we're going to capture that oxygen gas and then use some stoichiometry to figure out how much KClO3 was in our original unknown sample, how many grams of KClO3. And so we capture So what we need is we need the pressure of the oxygen gas, we need the volume of the oxygen gas, we need the temperature of the oxygen gas, and then we can calculate the moles of oxygen gas. From the moles of oxygen gas, then we can get the grams of oxygen gas. Or actually, we don't want the grams. From the moles of oxygen gas, we're going to calculate the moles of KClO3. And then from the moles of KClO3, we'll calculate the grams of KClO3. So we have to determine the pressure of the pure oxygen, the volume of the pure oxygen, and the temperature of the pure oxygen gas. And then once we get the grams of KClO3, then the percent KClO3 by mass is just equal to the grams of KClO3 divided by the grams of unknown, which is the white solid, minus, or no, not minus, times 100%. This is, we'll call calculation 1. There's calculation 2, which requires us to take all these mass measurements. So the mass after reaction minus the mass before reaction is equal to what? Okay, so the mass after reaction, what do we have in the test tube now? We have KCl plus inert stuff. Plus the oxygen. But what happens to the oxygen gas? The oxygen gas escapes from the test tube. The mass before the reaction is equal to KClO3. Actually, I have this backwards, but it's fine. Plus the inert stuff. The inert stuff doesn't react. So I should do this. I should do the mass before the reaction minus the mass after reaction. And do you know what that's going to give me? It's going to give me the mass of oxygen gas that was lost. So the difference in the mass before and after, the after we're missing the oxygen gas. If we know how many grams of oxygen gas, then we could go to moles of oxygen gas. From moles of oxygen gas, we could go to moles of KClO3. And then from moles of KClO3, we can go to grams of KClO3. And then we're going to calculate the percent KClO3 based on calculation 2. This is just the grams of KClO3 divided by the grams of unknown times 100%. And then we're going to compare the percent that we calculated from calculation 1 versus the percent we calculated from calculation 2. Calculation 1 and calculation 2 should give us this exact same percentage KClO3. And so let's see how close they come out. Most people get it pretty close, you know, not exact, but pretty close. For sure, calculation 2 is a heck of a lot easier, you know, than calculation 1. Calculation 2 is a heck of a lot easier because we just weigh everything before and we weigh everything after. We'll just subtract it. And so by far, calculation 2 is, if we did just calculation 2, this experiment would be done so fast. 20 minutes, we'd be done. But since we're doing calculation 1, it's not so easy. Since we're doing calculation 1, we got to take all these measurements here. And taking those measurements is a bit of a pain. And so we'll talk about taking these measurements here for calculation 1. So this is the experimental apparatus you're going to use here. So let me talk about setting it up. Here's our KClO3. It's not pure KClO3. It's KClO3 mixture with the inert stuff. It would work if it's pure KClO3, but then we'd know it's 100% KClO3 from our calculations. Plus MnO2 catalyst. Ignition test tube. We're not going to ignite it. We're just going to heat it up. We don't want it to ignite. We don't want it to explode. There are certain compounds that are quite explosive. Oxygen, you know, in the form of oxide, O2 minus, is not a good reducing agent. You know, oxygen is a great oxidizer, which means its conjugate, which would have oxygen in the -2 oxidation state, is a very poor reducer. But there are certain compounds that are actually pretty good. I don't know if I had it on this one. No, I didn't have it on this one. Let me get the other one. Number 24, which species is inherently unstable? And when we look at potassium permanganate, potassium permanganate is very reactive. But, you know, this is like, if potassium permanganate is like, let's see, how would you liken it? Maybe like a predator. Let's say potassium permanganate were a predator and it's seeking electrons. If you were a source of electrons, a source of food or fuel for the predator, then that would be a dangerous situation. But if you just had like a room full of predators, then there's no prey, correct? And so it'd be stable. And so potassium permanganate is like a predator, but if there's no prey, it's stable. And so we don't really worry about it reacting with anything because there's nothing to react it with. However, there is, you know, potassium ions, no. You know, when we look at potassium permanganate, what do you think? You think the manganese. Why do you think of the manganese? Because the manganese is what oxidation state here? Well, potassium is +1. We do that first. Group 1 goes first. And then which would go next, oxygen or manganese? Oxygen would go next at -2. And then manganese would be +7. +7 is a very high oxidation state. That means this is extremely electron poor at +7. This is going to be a powerful oxidizer. It's going to be a powerful oxidizer, but is it going to oxidize the oxygen? No, it shouldn't oxidize the oxygen. Maybe if you heat this up to very high temperatures, if you heat it up to very high temperatures and maybe throw in some catalyst in there, yes, then it's possible, right? But nah, it's like potassium chlorate. You know, I'm not going to have an explosion shield here protecting myself. This is potassium chlorate in here. In fact, I'll shake it up, and I'm not going to worry about it exploding here, because I'm really not going to worry about chlorine and oxygen. Right? And the same thing with potassium permanganate. If I had some, I'd shake it up, no problem. I wouldn't worry too much because the oxygen's happy as is. You know, this is like trying to oxidize. You know, if you think about water, hydrogen in the water could be an oxidizer, and oxygen could be a reducer. Hydrogen's +1 in water, oxygen's -2. So can the hydrogen take electrons from the oxygen? No, it's not really going to happen. Could it happen? Yes, it could happen. You know, maybe at extreme temperatures. At extreme temperatures, you'll have hydrogen elemental and oxygen gas, hydrogen gas and oxygen gas. Or you could do it forcefully by using electricity. It's called electrolysis, and then we can generate hydrogen gas and oxygen gas from water by forcefully transferring the electrons from the oxygen to the hydrogen. But this isn't going to happen. So yeah, if we have a room full of predators with no prey, nothing's going to happen. Nobody's going to get eaten. However, if you look at this is different. When you look at ammonium, nitrogen here is in the -3. Well, what do we expect for nitrogen? Nitrogen's charge varies from what to what? +5 to -3. So now what you have is you have two nitrogens. Which nitrogen's stronger? Is nitrogen versus nitrogen. One nitrogen is rich with electrons. The other nitrogen has no valence electrons at all. What do you expect? Is this a stable situation? These are two nitrogens. What do you think might happen if those two nitrogens come into contact with one another? Then one of the nitrogens might get in a tug of war with the other nitrogen. If two nitrogens get in a tug of war for electrons, which nitrogen wins? The left nitrogen or the right nitrogen? Or if you had two nitrogens in a tug of war, which one would win? Uh-huh. Well, no, the carbon, when it's fully maxed out, is somewhat stable, but we have to, that's what we have. When we study chemistry, chemistry is a combination of theory. Theory is these numbers, and observation. And so what we have to do is we have to correlate these numbers with some sort of observation. And the observation is a comparison of compounds. So when we look at something like CO2, CO2 is maxed out, but is it a very strong oxidizer? And that comes from observation. We exhale CO2 with every breath. Are we worried about oxidizing anything? Are we worried about combustion occurring because of that? In fact, we use CO2 in fire extinguishers. If we use CO2 in fire extinguishers, aren't we fanning the flames, adding more oxidizer? Fanning the flames means add more oxygen, more oxidizer to the fire. And CO2, no, it doesn't do that. CO2 is a poor oxidizer, unless it's a metal. Do not use CO2 fire extinguishers on metal fires, because CO2 is an oxidizer and metals are great reducers, and you're going to just fan the flames. So, you know, this is why firefighters are interested in redox, especially, yeah. But for nitrogen, it's a different story. +5 is not so stable. +4 on carbon is stable, and so this is just from observations, from just this is what people call experience. You know, there's experienced mechanics. They have 30, 40 years of experience working on cars and this kind of stuff, and they can diagnose things quickly or figure things out. But, you know, you're chemists, so you're trying to cram like hundreds of years of experience into one semester, basically. That's what we're trying to do in this, you know. But anyway, going back to this, here, now, if there's a tug of war, which one should win? They're both nitrogens. So what's going to happen is they're going to react. This is an unstable situation. It's an unstable situation because you have ammonium, which is a great reducer, and nitrate, which is a great oxidizer, in the same compound. What's keeping them from reacting? What's keeping them from reacting is they're locked in their lattice position. So as long as they stay in their lattice position, they're all right. But what do you think is going to happen if you heat this up? If you heat up ammonium nitrate, then, yeah, you're going to get the kinetic energy. And if an ammonium hits a nitrate hard enough, then there's going to be instant reaction. There's different ways. Like, so, for example, I wouldn't expect this to be mechanically stable. So if I had ammonium nitrate in this, I wouldn't be grinding on it with a stir rod. Because what happens if you're grinding on this with a stir rod or something like this, you can push the ammoniums into the nitrate, and if they get too close, what's going to happen? Reaction. And so there are two ways to get ammonium nitrate to explode. One is mechanically, just compressing it, or two, heating it up. And so ammonium nitrate is an explosive, and it used to be a very dangerous explosive. It still is very dangerous explosive. So, like Beirut, Lebanon. That was an ammonium nitrate explosion that caused that huge devastation there. In China, Oklahoma, a whole bunch of ammonium nitrate explosions. And so this stuff is inherently. So in this, we have the predator and the prey in the same compound. Over here, we just have predator. Over here, this is just going to be predator. Over here, this is predator. This is a very weak predator. This is, out of these, this is a very strong predator. This is strong. Nitrate's very strong. And so this stuff is dangerous. And so we're doing a very unusual one. You'd expect the same thing. Like if we had lithium chloride, if you heat this up, you got to be careful because, maybe the chlorine could oxidize the oxygen in this. CO2, I wouldn't really worry too much about it. Permanganate, maybe, yeah, there too. You got to worry when you heat it up. But this one won't take nearly as much heat, ammonium nitrate, as the others. But we have a catalyst, and the catalyst is going to help speed things up. And so the setup here is, okay, once we know how much everything weighs, and you might want to weigh the test tube too in case you accidentally spill some stuff on the outside. So there are different ways you can do this. And we're going to set up our apparatus here. And so we're going to use a ring stand and a utility clamp here. And so what we'll do here is we're going to put the utility clamp at about a 45-degree angle. And so there's a little lock nut here. You can adjust the angle here. Once you get the angle to about 45 degrees, you could lock it by turning it clockwise. All right, and then with the utility clamp, you need to clamp this at the very top of the test tube here. Like this. I'll get rid of this cord. And so what I usually do is I just pinch it, and then there's a little wing nut. I'll try to spin the wing nut. Goes fast. This one doesn't spin so nicely. So I have it set up like this. You don't want it vertically. You want it at an angle. It's still not tight enough. And the reason is because heat rises. And so we're going to be heating the bottom here. But if you look at the utility clamp, there's these rubber or plastic coating on the arms of the clamp. And what people do is sometimes people clamp it in the middle or near the bottom. If you clamp this near the middle or the bottom, it gets so hot that the rubber starts to burn. And have you smelled the burning rubber or burning plastic? It's full of carcinogens, mutagens, and that kind of stuff. We don't want to inhale that because it's bad for our health. And so if you start smelling that next to you, and you see the person next to you has a clamp down here or over here, then tell them. We don't want to clamp it vertically because the heat's going to rise and it's just going to melt this stuff and burn it. Okay, so the oxygen is going to be generated and we have to capture it. And the way we're going to capture it is we have this apparatus here that we're going to use to capture it. And so we're going to seal this with a stopper. This is just a rubber stopper. We have to make sure the seal is very tight here. So any oxygen gas that's generated will feed out through this tube here. We have a glass tube that goes into this rubber tubing here. This has to be tight because sometimes what happens is the oxygen gas is generated quite quickly because of the catalyst, and it pops off the stopper. If it pops off the stopper, then you have to start over again, because now the oxygen gas has escaped into the room. What we want to do is we want to make sure the oxygen gas gets trapped. And the way we're going to trap it is by using a water trap. And the water trap is going to be in this Florence flask here. So we'll have a 500 milliliter Florence flask. And tap water is fine for this. I mean, it would be better to use DI water because there's we don't know what's in the tap water, and it could react with the oxygen gas. Let's say if there's anything that takes or consumes oxygen, like things that take or consume oxygen, or like biological material or whatever. But we're going to use just tap water. And so we need to trap the oxygen in this. And the way we're going to trap it is by water displacement. And so we have to set this up first properly. So before I stopper this, let's flip the camera this way here. Before I stopper this, I'm going to put this in here like this. And so this is it. So as we capture the oxygen gas here, what's going to happen is the oxygen gas is going to bubble to the bottom of the Florence flask and then rise. As it rises, then it's going to push out the water in the flask here. There's another tube here. It's going to push out the water here. But the problem is there's a bunch of air in this tube here. And what we're going to do is we're going to measure how much water gets pushed out. The amount of water that gets pushed out should be the same as the amount of oxygen gas that's generated. Right? And so what I have to do is I have to get rid of all the water in here, Otherwise, as the oxygen gas is being generated, it's pushing air and then water out the tube, and all that air we aren't going to capture, we aren't going to measure. So I'm going to have a beaker here that I'm going to fill up with water as well. Here. And then I have this set up here. And then what I'm going to do is I'm going to blow the air out of that tube. And so this is going to require a pipette bulb. Usually we don't blow things out with a pipette bulb, but in this case I'm going to blow the air out of the tube here using the pipette bulb here. So let's see. So I'm just putting the pipette bulb on the other end, the opposite end, and I'm just going to squeeze it. I still have air in there. Oops, this is not so easy. Okay, once we blow out some of the air, then I'm going to siphon the water. I can siphon the water back and forth. Actually, I have too much water in here. Dump some of that. It's not siphoning, so let me try this one more time here. The other way you can blow, this is the way that's they recommend in the lab procedure, is to cup your hand over the stopper and then just blow. I see something that's wrong here. You can check your apparatus, but the tubes are placed on the wrong ends here. You have to be very careful removing the tubes. This is where most accidents occur. And so if your tubes are on the wrong end here, then maybe let me do it or the stockroom do it, because what happens is people try to remove the tubes, they end up breaking the glass and cutting themselves. But this wasn't working because the tubes were on there backwards. Okay, let's try this one more time. So as the oxygen gas is being generated, it should go to the top of the water here. So the oxygen gas is being generated, it's going to the top here, and it's going to push the water down and then out this tube on the bottom. I'm just going to displace the water there. So this is what I'm going to do here. Okay, there's no more bubbles coming out there. And so what you can see is I have two water levels here. And what you should be able to do is you should be able to siphon water back and forth. Do you see the level in the flask rise? Okay, then I'll drop this, and do you see the water level decrease? I should be able to do this, siphon water back and forth. So what we're going to do is we're going to siphon water almost to the top. I like to get it very close to the top. There. And then this is going to require some so I'm going to get it just about to the top here and then hold it. So I got it, oops. You give it a twist to make sure it's tight. So let me re-siphon the water back up. And then I'm going to hold it to about where the level I want it at. Here, let me move this. Which is near the stopper here. And then I'm going to seal this. So I need it just below the stopper because I have to do one more thing. Okay, so now I've trapped the air. And so there's air trapped from here down to the top of this flask. So as the oxygen's being generated, what's going to happen is it's going to push the air out here, which is going to fill the top. So I have a bunch of air trapped in here. So as the oxygen's being generated, it's going to add to that gas here and push this down. And so we're going to treat this as an Avogadro's mixture. In an Avogadro's mixture, the volume of air plus the volume of the oxygen will equal the total volume. In order for Avogadro's law to work, we need to make sure that what stays constant? Pressure. So in order for pressure to stay constant, I have to do this. I have to equalize the pressure each time I do this. And so the first thing I'm going to do is I'm going to equalize the pressure of the air trapped inside here with the air outside in the lab. How do I do this? How I do this is like this. Do you see it's sealed here? Now I have air trapped in here. As I rise this up, do you see what happens to the water level in here? It goes up. And what that does is it compresses the air inside here. So if I try to siphon water back into the flask, it's compressing the air, and the air pressure is higher than the atmospheric pressure. In other words, if I take a look at the levels here, the water level for the air trapped in here and the atmospheric is up here. So that means the water down here is levels lower than the water level up here, and that means the air in here weighs more than the atmosphere. If I drop this down, do you see the water's trying to siphon out of the flask? That's creating a vacuum here. So that means that the atmospheric pressure down here pushing down on the beaker is heavier than the air pressure trapped in here. And so what I need to do is I need to get just the right amount, not too much water, not too little water. Too much water creates pressure, higher. Too little water creates a vacuum, lower. And so what I'm going to do is I'm going to equalize the pressures. To equalize the pressure, I make sure the weight of the atmosphere is equal to the weight of the air trapped in there by equalizing levels here. Do you see that? And then I have just the right amount of water trapped in there. Okay. So what I need to do is I need to equalize the pressures, and then what I'm going to do is I'm going to pinch the tube here. There are two ways you can pinch it. One, you could use a clamp, or two, I'll just pinch the hose. So I just pinch the hose there, and that's going to trap the water so no water can leak out or no air can get sucked in. And then what I'm going to do is, with this excess water here, I'm just going to dump it into the sink. Okay, and then I'm going to put the tube back in here. Now I don't care if water leaks out of this. It's not important, because any water that now comes out of this is going to be caused by the air and oxygen pushing it down here. Okay, then I'm going to get a burner. And you want to control this reaction. So just get a nice little cone on there, but I don't want to hit the tip of the cone on there. What I want to do is I want to heat it on the soft part. There's no catalyst in here, so that's why it's still white. Yours is going to look gray. And then heat it on the soft part. I don't want this to decompose yet, because I'm going to use it in the afternoon. Okay, once you'll see it start to react slowly. If it's starting to react too fast, that is, it looks like it's boiling and erupting, then back off the heat. And so you're going to hold this with your hand and then heat it up gently. Don't heat the rubber here, otherwise it's going to stink up the lab with toxic chemicals. You don't want that. And so just heat this gently, and once it starts to react and then it starts to slow down, then you can heat it more vigorously. But make sure you heat it all over to get everything to decompose. And so you're going to keep heating it until it looks like absolutely nothing's happening. You're not going to remove the stopper here. I'm going to remove the stopper to pretend that I'm generating. And so what's going to happen is the water level is going to go down in the flask, and it's going to fill up the beaker. Hopefully we don't generate too much oxygen gas, because if you generate too much oxygen gas, then what happens is the water level goes below this tube here, inside here, and then we get something like this. So let's say we generated this much, and we can see by displacement of water how much that is. But in order for volumes to be additive, according to Avogadro's law, the pressure has to be constant. So we have to do this again, because we can siphon water back and forth depending on the relative position of the beaker. And so what we're going to do is we're going to match the two water levels. When we match the two water levels, that's just the right amount of water in the beaker. And so this will be the volume of oxygen gas that's generated. That's going to be wet oxygen gas. And so what I'm going to do is I'm going to match the two levels there. And that has just the right amount of water. And then I'm going to pinch the hose. You could use a screw clamp like they say, or just pinch this like this. And then that's it. That's how much oxygen I just generated. And then I'll just take this to a grad cylinder and then measure how many milliliters of oxygen gas I generated. Since the air was already in here and we already compensated for it, that's just the oxygen that displaced this, because the volume of air is already here, and then any additional volume will push the water out into the beaker over here. And so this is the volume of oxygen gas we generated, but the oxygen gas is not pure. Since the oxygen was bubbled through water, it's been saturated with water vapor, so we call it wet oxygen. And so what we'll end up with is the volume of wet oxygen. Let's see. It is here. So the milliliters of the H2O liquid is going to give us the volume of wet oxygen. Okay, then we need to measure the pressure. of the wet oxygen. And since we equalize the pressure with atmospheric pressure, we're going to measure it using the barometer. The barometer is mounted on the wall next to the fire alarm. And so you're going to go over there and then measure the pressure on the barometer. If you go take a look at the barometer, on the left side we have inches of mercury liquid. On the right side we have millimeters of mercury liquid. And so we're going to be measuring the millimeters of mercury liquid. The mercury is in a glass tube, and it's going to have a convex meniscus. Mercury hates glass, so it tries to minimize its contact with the glass. Versus water. Water loves glass, and as it tries to maximize its contact with it. And then there's a scale on the right, you know, this. So let's say today's a pretty nice day. Let's say this is 760, this is 761. So normally what we would do is we'd estimate it by taking a look at where it lands. This one looks like it's 760, what would you say? 0.7, 0.8, something like that. That's what you do normally, but with this we have a vernier scale that's imprinted, and with the vernier scale what it does is it just reads the last digit so you don't have to guess it. And so we're going to use the vernier scale to read the last digit. The vernier scale is located on the barometer directly in front of the tube. Let's see. Let's do it over here. So there's a metal slide located on the balance. And there's a knob on the side of the balance. Is there a knob on that one? No, there's no knob on that one. What we can do is we could slide the vernier scale. This is the vernier scale here, up or down. And what we want to do is we want to line it up with the meniscus here. And so we slide it down so that the bottom of the vernier scale matches the top of the meniscus. And then what you do is you look at the vernier scale, and the vernier scale is going to be printed like this. There's going to be a 0, 5, and then a 10 mark here. And then look for any line on the vernier scale that matches a line on the barometer. So, for example, it looks like the 7th line on the vernier scale matches with the line on the barometer. And it doesn't matter what the lines here are, the numbers. We don't really care about that. We're just looking at this line here. What I mean by matches is we go across left to right like this. This one's offset, 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 offset. And so only one of these lines will match. And so if the 7th or 8th line, let's say the 7th line here, matches with one of the lines to the right, then that's the last digit. So the reading here would be 760.7 millimeters of mercury. So by using that scale, we don't have to guesstimate this. Rather, it's much more precise. We can use this to get that last digit. Is that clear? This? Okay. All right, so that's the pressure. And finally, the temperature of the wet O2. The temperature of the wet O2, we just remove the stopper, take our thermometer, and just measure the temperature of the gas inside here. And that will give us the temperature of the wet O2. And so those are the measurements we're taking for this experiment. The pressure using the barometer, the volume using the amount of water that was displaced under constant pressure conditions. This has to be under constant pressure conditions. And the temperature. And so it's not too bad. And then all the masses. All right, any questions on this? I'm sorry?
We're going to be able to finish this whole lab today.
Yeah. The lab, I mean, most people can finish in like 30 minutes, I think. But I don't know. Are you doing one trial or two trials? Just one trial? Yeah. 30 minutes to an hour. It should be plenty of time. How to get the air out of the tubes? All right. To get the air out of the tubes, you're going to fill this Florence flask full, and then a beaker, like half full. And then there's going to be air trapped in here, but before we do that, we got to make sure we purge the air out of the apparatus. To purge the air out of the apparatus, we're going to seal it here, and then we're going to blow it. You can blow. I used my mouth, but you could use this. The problem. This is working fine now. If I use two hands to create, I got to create a seal here. And then all you want to do is you want to keep an eye to make sure there are no more bubbles coming out. And then siphon water back and forth just to make sure that there's still no bubbles coming out. And so I can siphon water back into the flask and siphon water out. But what I need to do is I need to fill up the flask close to full and then seal this and then equalize pressure. I think we're working in groups today, so you can work in a group of 3, up to 3 if you want. 2 or 3. Okay, we're good. I can help you if you need additional help.